All right, let's talk about data. We're surrounded by it, right? Every chart, every statistic, they're all screaming for our attention. But here's the big question. How do we know what's a real pattern, a genuine discovery, and what's just, random noise? Well, today, we're going to pull back the curtain and look at the secret tools statisticians use to separate that signal from the noise. Let's get right into it. And this, right here, is the question that's at the heart of everything. You see a result. Maybe it's a poll or a new study or your company's sales figures. Is that a real, meaningful pattern? Is that a signal? Or is it just a statistical fluke? A bit of random noise that honestly doesn't mean a thing? And believe me, telling the difference is absolutely crucial. Okay, let's make this super concrete with an example straight from the source material. Picture this. You're running a test and you're expecting a 50% success rate, like a perfect coin flip. But you run it 100 times and you only get 45 successes. So what do? Is 45% close enough to 50% that it could just be random luck? Or is that 5-point drop a red flag, a sign that something is actually different than what you expected? So how in the world do we answer a question like that? Well, we act like a detective. We're going to take that 45% result, put it on trial, and see if the evidence really holds up. Now, the very first step in any statistical investigation is to state something called the null hypothesis. The easiest way to think about this is innocent until proven guilty, but for data. We start off by assuming the most boring, the most skeptical explanation possible. We assume there's nothing special happening here. For our case, that means we assume the true success rate really is 50%, and that 45% we saw? Just a random fluke, just bad luck. And this is where it gets really interesting. We have to imagine a world where that skeptical view is actually correct, a world where the true rate is 50%. Then, from inside that world, we ask a simple question. How surprising is it to see a result of 45%? Is it a no way, that's 1 in a million kind of surprise? Or is it more of a, yeah, that happens sometimes kind of result? Measuring that level of surprise, that's the whole game. Okay, so that's how you tackle a simple percentage. But what if your question is totally different? Because, it's not always about the average value. Sometimes the real story, the juicy stuff, is hidden in how consistent, or maybe how inconsistent, the data is. So let's jump into our second case study here. Imagine you're looking at some data from, let's call it Group Y. You can see the data points are all bunched up. They're really tightly packed together. Right away, that tells you this group is super consistent. It's stable. It's predictable. But now, take a look at this second group. Wow, the points are just all over the place. It's the total opposite. Inconsistent, spread out, volatile. Just looking at it, it's pretty obvious these two groups are behaving very differently, right? But can we actually prove that with math? Can we put a number on it? You guessed it, we're going to use the same playbook. We start with our null hypothesis, that boring, skeptical starting point. We're going to assume that, hey, despite what our eyes are telling us, both of these groups actually have the exact same amount of spread, the same volatility. Any difference we think we see? Nope, just random chance. So to test this idea, statisticians calculate something called an F-statistic. It sounds fancy, but it's really just a simple ratio comparing the spread of the two groups. The data from our source gives us a value here of 2.79. What does that mean? It means the messy, volatile group is almost 3 times more spread out than the stable one. Now, that feels like a huge difference, right? But is it big enough to be what we call statistically significant? And this is how we get the final verdict. That F-statistic, that 2.79, gets plugged into a formula to calculate something called a p-value. And you can just think of the p-value as our flukometer. It tells us the exact probability of seeing a difference this big if the null hypothesis were true, if the groups really were the same. So what's the number? It's 0.0012. That is a tiny number. We're talking a 0.12% chance. So the odds of this being a random fluke are incredibly low. So low, in fact, that we can confidently reject that boring skeptical idea and say, nope, these groups are definitely different. All right, so let's pause for a second. We just looked at 2 pretty different problems, right? One was about a single percentage. The other was about comparing the spread of 2 different groups. But, and here's the big reveal, behind the curtain, we were using the exact same 4-step recipe for both of them. And this is it. This is the statistician's secret recipe. It's a universal framework. Step 1, you state the null hypothesis. That's your nothing is happening here assumption. Step 2, you state the alternative hypothesis. That's what you're actually hoping to prove. Step 3, you calculate your test statistic. That's you boiling all your evidence down into a single number. And finally, step 4, you find the p-value to make your decision. That's the verdict. Was it a real signal or was it just random noise? Now listen up, because this is probably the most important part to get right. The p-value is not the probability that your theory is true. I'm going to say that again. It's not the probability your theory is true. It's the probability of seeing the evidence you saw, assuming the skeptic was right all along. So a really small p-value just means your data looks super weird and surprising from the skeptic's perspective. And if it's surprising enough, you have good reason to say, you know what, I don't think that skeptical view is correct. Let's bring it all together and see how this one recipe works everywhere. In our first case, the test for a single percentage, what was the skeptic's claim? The true rate is 50%. In our second case, the F-test, what was the skeptic's claim? The groups have equal volatility. And the sources we looked out even mentioned another one, a chi-square test for some economic data, where the skeptic's claim was the variance is 0.1. See the pattern? It's always the same logic. You start by assuming the skeptic is right, and then you check to see how much your evidence surprises you. It's beautiful, really. So I hope you see this isn't just some abstract academic exercise. This whole framework, this idea of separating a true signal from random noise, it's honestly one of the most powerful tools we have for making smart decisions in the real world. Think about it. Every single time a company does A/B testing on their website, they're using this framework to see if that new button color actually made a difference. Every new drug that comes to market, it had to go through clinical trials that proved, using this exact logic, that its effects weren't just a fluke. We're talking about everything from quality control on a factory floor to evaluating major economic policies. This is the engine that drives evidence-based decisions. And at the end of the day, that's the real takeaway here. Understanding this process gives you a completely new lens to see the world through. It's a toolkit for challenging claims, for pushing back on headlines, and for avoiding getting fooled by what looks like a pattern but is really just randomness. It's about knowing with some confidence when a result is real and when you should probably stay a little bit skeptical. So, the next time you see a headline or a chart that's making some big, bold claim, you'll know exactly what to do. Before you even ask yourself, is this true? I want you to ask a different question first. Compared to what? What's the boring, skeptical assumption here? What's the null hypothesis? And just how surprising is this evidence really? Once you start asking those questions, that's when you started to think like a statistician.